follows what's called a great circle. So, for example, this great circle line between Washington and Mecca is quite different to what you might expect. So the direction to Mecca from Washington actually points slightly northeast rather than southeast. Of course, this is complicated stuff, but the key point for Islamic scholars is that knowing the direction to Mecca requires a knowledge of how steeply the earth curves. And that means knowing how big it is.
So Al-Ma'mun commissioned his very best scientists to measure it.
Hello.
Hello.
Mr. Sami. I'm Jamal Khalili. Nice to meet you.
To understand how they did it, I'm meeting up with Professor Sami Chaloubi from Aleppo University in Syria, who's an expert in early Islamic science.
Come and join me.
Professor Chaloubi began by explaining the measuring technique, which Al-Ma'mun's scientists first used and which they had inherited from the Greeks.
We're now talking about the earlier Aristophanes technique of measuring the circumference. It was repeated again by the Abbasid astronomers, was to measure the distance between 2 points and then look at the angle of inclination of the sun. So in Egypt, in Aswan down in the south, they regard the sun as being vertical. This is near to the equator. And they worked out how far away from the vertical the sun was if they measured it from the north of Egypt in Alexandria, which is on the Mediterranean coast.
Al-Ma'mun's astronomers repeated the Greek experiment in Syria and Iraq by measuring the angle of the sun in the sky at noon at one known location. They then walked due north to a second location, carefully measuring the distance they travelled. At the second location, they once again measured the angle of the sun at noon. This angle would have been slightly smaller than the first one. With these figures, Al-Ma'mun's astronomers were able to estimate the Earth's circumference. They got a value of 24,000 miles, within 4% of the correct value. Not bad, you might think, but this method was flawed and ultimately unreliable. The main problem with it was that measuring the distance between two locations was incredibly difficult. It could only be done by the unreliable method of counting paces as you walked through the burning desert. A more reliable and sophisticated method for estimating the Earth's size was needed, and 2 centuries after Al-Ma'mun died, it came. What made it possible was a great leap of imagination, and the fact that by 900 AD, much of the world's mathematical knowledge had been translated into Arabic, so scholars could scrutinize and improve on it.
Out of this obsession with scholarly learning came a true mathematical visionary, Abu Rayhan Muhammad ibn Ahmed al-Bayruni. And like all Islamic scholars of the time, al-Bayruni was obsessed with the science and mathematics of the ancient Greeks, Babylonians, and Indians. And because of the success of the translation movement, he had literally on his desk the great work on geometry by Euclid, Ptolemy's Almagest, the Indian text, the Sinhind, and the famous work on algebra by Al-Khwarizmi.
Professor Chaloubi has brought along the book in which al-Bayruni describes how he combined algebra and geometry with some very simple and practical measurements to solve the epic problem of how to calculate the size of the Earth.
Bayruni, the text.
This is his the Mas'udi canon.
Yes.
This is Bayruni's canon, which I've been trying to get hold of, where he describes this fantastic experiment. And oh, you found the page.
Yes.
Having read al-Bayruni's description of how to estimate the size of the world, I wanted to try it for myself.
First, he had to find a fairly high mountain from the top of which he could see a flat horizon. In this case, the sea.
What I love about this story is that with a few simple measurements around this small mountain peak, you can work out the size of the whole world. Al-Biruni's first step was to work out the height of the mountain. He did this by going to 2 points at sea level, a known distance apart, and then measuring the angles from these points to the mountaintop.
So, to measure the angle to the mountaintop, Biruni had to use a device like this, called an astrolabe. It's basically a giant protractor. It has the angles in degrees marked around the outside, and a pointer to help him determine his line of sight. So if we try now and determine the angle to the top, it has to hang freely, and then, okay, so if you let it hang.
I'd like to stress, if you haven't noticed already, that Al-Biruni would have made his measurements more meticulously than I am. He did them again and again to get consistently reliable results.
Okay, that's about it. And that is 24.5 degrees. Okay, so now we've determined one angle. We now have to go and pick our second spot along the beach.
The distance from the first to the second point must be measured accurately. In this case it's 100 meters, and the 2 points must be in a straight line with the mountain. I measured the second angle to be about 26.5 degrees, and now had enough information to calculate the height of the mountain. Using trigonometry and algebra, Al-Biruni used a formula that relates the height of the mountain to what are known as the tangents of the angles he measured. Using my measurements, I get a figure for this mountain of about 530 meters. I now need only one more measurement to get the size of the Earth. And to get that, I have to climb to the top of the mountain.
What Biruni did next was measure the angle of the line of sight to the horizon as it dips below the horizontal. So we're going to try and reproduce that. So if you can lift it up so that it's hanging, and if I locate the horizon, okay, which is about 0.5 degree, which is about the value that Biruni got. Now here's the really ingenious part. Biruni had measured 4 quantities, 3 angles and a distance. He used 2 of the angles and the distance to work out the height of the mountain.
Al-Biruni now had everything he needed. In essence, Al-Biruni imagined a huge right-angled triangle which has as its 3 corners the mountaintop, the horizon and the centre of the Earth. Trigonometry told him that the angle he had measured and the height of the mountain are related to the radius of the Earth, and algebra allowed him to calculate it.
With this formula, Biruni is able to arrive at a value for the circumference of the Earth that's within 200 miles of the exact value we know it to be today, about 25,000 miles. That's to within an accuracy of less than 1%. A remarkable achievement for someone 1,000 years ago. For me, Biruni's experiment is an early dramatic example of a scientist using mathematical reasoning to extend humanity's reach. He really pushes the idea that abstract geometrical rules governing idealized shapes like perfect circles and triangles can help us to comprehend the real world. Einstein used precisely the same approach, admittedly with much more advanced mathematics, when he developed his general theory of relativity almost 1,000 years after Biruni. But both Einstein and Biruni were united by a single common idea. With mathematics, humanity can embrace the universe.
In this story of the birth of the scientific method, the Islamic scholar's ability to master sophisticated mathematics is the first crucial ingredient.
The second crucial ingredient is the use of experiments in science. Without experiments, theory remains meaningless and sterile. It's experimentation that allows theory to be held up against the real world. It gives it physical meaning. But whereas sophisticated mathematics grew out of the empire's obsession with the world's learning through the translation movement, practical experiments came from the daily needs of a powerful and expanding civilization.
The driving force of the expanding medieval Islamic empire was trade. It boomed from around 700 AD onwards, creating a massive demand for metal workers, glass blowers, tile makers, craftsmen of every possible kind. When this collided with scholarly tradition, symbolized by the translation movement, it had seismic consequences for science.
The sciences absolutely depend, astronomy is a wonderful example, chemistry is another, on really intense relationships between craft traditions of instrument making, of working with metal and fire, of working with medicines, drugs, plants, and scholarship, highly sophisticated literary and mathematical analysis. And the Islamic world is just such a place.
By around 800 AD, the great cities of the Islamic Empire dominated the world's trade. To its markets came silks, spices, drugs, fruit, perfumes and gold, from as far afield as India and China in the east and Spain in the west. Anything that could be traded was. A wonderful relic of this medieval trade boom are the great caravanserais, like this one in the Syrian capital, Damascus. This huge vaulted building was designed as a resting place for all the traders and their animals who visited the city. On their ground floors were wide spaces for animals and goods. And above there were rooms for the rich merchants to refresh themselves before another day of haggling. One 10th century traveller talks of the riches and beauties of the bazaars, and that the income of the provinces and localities was between 700 and 800 million dinars. Markets like this in the Egyptian capital Cairo still capture the intensity of medieval trade. And still surviving in the modern world of the internet and the mobile phone is a fantastic example of how traders 1,000 years ago communicated across a vast empire.
So this is a carrier pigeon, its base is here, so wherever you took this pigeon all over Egypt, it will make its way back to this guy. There's a famous story that a rich Cairo merchant by the name of Anur wanted to grow cherry trees. So he sent a message with a carrier pigeon to a contact of his in Damascus asking for some seeds. His contact sent back 500 birds, each one carrying a small bag with seeds in it. The whole process took just 3 days. Sort of a medieval FedEx, really.
By 700 AD, the Islamic Empire was taking the first steps towards mass production.